Shown in the figure below is a submarine chasing a squid. Luckily for the squid, he is moving faster. The submarine emits a sonar pulse with a frequency of 12,000 hertz. Using 1450 meter per second as the speed of sound in water, find all the following: the frequency heard by the squid, the frequency heard by the sub reflecting off the squid, and the beat frequency between these two. This problem involves the Doppler shift. It's unlikely that the sign convention I'm about to tell you regarding the velocity of the listener and the velocity of the source is similar to your textbook. The reason is, each subsequent textbook comes up with a new convention for what one should call plus, each more complicated than the last, whereas the formula itself is actually extremely simple. The Doppler shift formula tells us the frequency as heard by the listener as compared to the frequency emitted from the source in terms of three possible velocities. One is the velocity of the wave itself, and the other two are velocities of the listener and of the source. Your book may have a difference in minus signs top and bottom. It may have absolute value signs. In fact, almost anything is possible going from one textbook to the next, because each textbook seems to make up their own sign convention for what one should call the positive direction. I find this particularly bizarre, because in fact I won't tell you a sign convention. You can select any direction as plus that you like, and this formula will work every time, as long as you remember the following: three velocities: velocity of the listener, velocity of the source, and velocity of the wave all have the possibility of being positive or negative in your chosen coordinate system. So long as you are consistent and select one direction as the plus direction, and examine both the motion of the listener, the source, and the wave as compared to this direction, and select either plus or minus for each one of these three velocities, this formula works every time, as is, no absolute value, and no trial and error. So let's begin our analysis of the problem. Part A asks us to find the frequency of sound as heard by the squid. This means that the squid will be the listener, the submarine will be the source, and the wave will be the sound moving through the water. Rewriting our Doppler formula, the only thing we need to do is supply the three values for the appropriate velocities. Now, since both the squid and the submarine are moving to the left, I think I'm going to choose to the left as the positive direction. What this means is that the velocity of the listener, which is the squid, is in the plus direction and is of an amount 20. The velocity of the source is the submarine. It is also in the plus direction, and it is of an amount plus 15. And finally, the velocity of the wave, since in this part of the problem it is going from the submarine toward the squid, is also in the plus direction. And that velocity is 1240. Plugging in all three of these velocities, we'll be able to solve for the frequency of the listener using an original frequency of 12,000 hertz coming from the submarine. The result of this calculation yields a frequency of 11,951 hertz. Exactly as we would expect, since the squid is receding from the submarine. Now let's solve for part B. In part B, we're to determine the frequency heard by the submarine after the sound has reflected off the squid. Again, we use our familiar Doppler equation. Although many textbooks might tell you that at this point you have to change the sign convention on your velocities, I'm going to tell you just the opposite. Since the squid and the submarine are moving to the left, I'm going to keep the left as positive, meaning that the velocity of the listener is the submarine, is positive 15. The velocity of the source, where the source is the squid, is positive 20. And the velocity of the wave, since it now goes from squid towards submarine, that will be our negative number. Velocity of the wave is negative 1240. As we plug in these numbers, we have to be mindful of what will be the frequency at the source. The source is now the squid. Even though the submarine originally released a sound whose frequency was 12,000 hertz, the squid never hears 12,000 hertz. The squid only hears 11,951, and so the frequency emitted at this stage in the problem is 11,951 as it comes off the squid, and in fact it will be even lower as it reaches back to the submarine. Plugging in the numbers, we get the result 11,903 hertz. Finally, in part C of the problem, we're asked for the beat frequency heard at the sub. What we know about beat frequency is that the frequency of beats, when you mix two waves of different frequency, is equal to the absolute value of the difference between the two frequencies. At this point in the problem, we need to ask ourselves, out of the three frequencies that we know of, 12,000 hertz, 11,951, and 11,903, which two of these are heard by a person on the submarine? The answer is that the 12,000 and the 11,903 are heard at the submarine. The 11,951 hertz is only heard by the squid, and no one on the submarine is subjected to that frequency. Therefore, when we take our difference to determine the beat frequency, we'll use the 12,000 and the 11,903 to get the result 97 hertz, as heard at the submarine.